Okay.
So thank you, Silviu, and go ahead with your talk.
Thanks for this introduction, and I'm really sorry for the small delay at the beginning of. I was not able to connect earlier, and I hope that we'll not have other interferences in terms of the quality of sound at my end. So the title is a little bit strange for such a talk. So delays, dynamics, and singularity tracking on the guided tour, and it's a joint work with some of my colleagues: Islam Busada from France, Guillermo Mazanti from France, Subangli from China, and Fernando Mendes Barrios from Mexico. So let's go directly to the next introduction. So the introduction is. It's unusual for let's say when we're talking about the delay, in the sense that I'm starting with Sherlock Holmes. In fact, the book from 1892. 1892, it's an important date in saying for everybody working in a dynamical system, because it's the book of Lyapunov devoted to the motion, to the stability of motion. So apparently in the same year, in fact, Conan Doyle published most of his novels during 91 or 90 at the beginning of the 92. And why the adventures of Sherlock Holmes? For two reasons. The first one is that singularity is almost invariable clue, and I think that it sounds quite nice. And the second one, it's another thought that I found quite interesting to share with you, is that it has been a long axiom of mine that the little things are infinitely the most important things. Okay, so let's leave Sherlock Holmes to other issues, and let's go ahead. Let's go ahead to our problems. So taking a look a little bit to the history, in 2006, Hale has written a nice, let's say, book chapter devoted to the history of delay equations. What it was funny that he, in his book chapter, he indicated the Picard's thoughts. Picard was given a talk at the beginning of the 20th century at the International Congress of Mathematics, and during his talk, he indicated that it will be a good opportunity to start taking a deeper look to everything related to heredity in a dynamical system, and in particular in differential equations related to mechanics and mainly biological systems. So I reproduce the text from the Hale chapter, and as well as the text from Picard, original presentation that it was in French, and I just underlined heredity and functional equations, the French wording. So of course we are not discussing about this. We are going a little bit more deeper in the stories, and let's say that although delays are almost everywhere, at least this is my vision, I'm not the only one. I hope that you are sharing the same vision with me. Everywhere in physical, chemical, and biological processes, delays in general may capture the specific dynamical behavior if we are talking about the heterogeneity of the temporal phenomenon. And I think that this is one of the things that perhaps should be emphasized a bit more inside our community, at least each time when we are discussing about modeling. So now, singularity and delays. So when we're talking about singularity in terms as a mathematical object, in fact, singularity is more or less, roughly speaking, corresponds to the cases when the object is not defined, or if the object is not well behaved. When we are saying not well behaved, it's a bit. Okay, we can enter into details to be more specific. What does it mean well behaved? What does mean not well behaved? So in general, we are talking about the lack of differentiability, lack of analyticity, since we are talking about delays, but we can talk also about changing the nature of the object. And in such a case, we can have several types of singularities that we can talk about and we can figure out. Okay, so now throughout this lecture, I will talk about delay dynamical system by using the delay differential equation representations that are simply called DDEs. And I will more or less discuss about some, let's say, singularities, typical singularities, and these singularities are related to the effects induced by the parameters, and in particular, the classical typical singularity are the multiple characteristic roots. So now, from the historical perspective, it's always delicate to figure out everything that it was written in the literature. There are more, at this stage, there are more than 50,000 papers, at least Google indicating more than 50,000 papers devoted to delay systems. I'm talking about by using delay differential equation representation. And with respect to that, if we are going back to the beginning of the 20th century, I realized that there are no any reference devoted to the in which there is an explicit discussion of the, let's say, multiple characteristic roots for the linear delay differential equations. And I found, together with my colleagues, more or less two references in which saying the point of view of multiple characteristic roots is explicitly taken into account. And so I'm talking about the paper of Hayes in the 50s, 1950, saying the beginning of the 60s, and Scalar on second order delay differential equations cases discussed in the book Pinay in 1958. The book of Pinay is more or less devoted to the so-called the stability, the decomposition method. So we are representing the stability regions in the parameter space under the assumption that the delay is constant. So this is the classical decomposition method introduced by Neymark in 49. And the terminology developed by Pinay in 58 is a little bit different from the terminology of Neymark. And there are a few results in the 70s and the 80s, and of course, it's difficult to mention all of them. But as a conclusion, there is no any systematic analysis, classification, characterization. There are some attempts. There are some nice results that we are we have used them, and but in our opinion, I'm talking in the name of the whole set of authors, co-authors of the paper, there is no explicit systematic analysis. Okay, so with this, what it was the initial intention of my guided tour is just, and I think I will say a little bit more on this slide, and after I will comment some of the issues related to it, and I will go ahead with a little bit some more introductory materials. In fact, this talk is more or less there is a complementary talk that I will give in a few days. It will be to the IFAC-TDS workshop, and I think that both G and Wim will talk about this after my talk, or this event after my talk. And the idea was just to have an introduction to the talk that I will give in to the TDS workshop, and not to have a more or less a copy and paste of the same presentation at both events. So there are more introductory materials here and more detailed material during the second talk. So now, when we're talking about a guided tour, in fact, the guided tour is more or less related to the methods, and during the last 10 years, I was focusing more or less on 3 approaches. One of them is by using the Variance preparation theorem in connection with the Puiseux's algorithm, Puiseux's series, and this is a particular way to characterize each time when we have multiple roots. And we can say that this is a standard methodology in the case when we have multiple characteristic roots. The second one is frequency sweeping curves and imaginary characteristic roots. So the idea of frequency sweeping curves is just to reformulate the problem of saying asymptotic behavior of the characteristic root, which are, let's assume that there are multiple on the imaginary axis in terms of curves, and by particular let's say examination or inspection of the curves and their intersection with a line having the ordinate equal to 1, we can detect how many roots are crossing from the left to the right and how many roots are crossing to the left. So in other words, we have a kind of signature of each characteristic root given by the number of difference between the number of crossing to the right and the number of crossing to the left, and we'll have a lot of exotic cases that may appear. And these exotic cases in general are, can be in some sense controlled by using the properties of saying by using some analytic properties of coming from number theory. But okay, this is not the aim of the talk. And when you're talking about invariance in this particular case, the idea is just to go ahead and to take into account concepts coming from, let's say, a generic theory of invariance, which is by using, for instance, Knop theory, and going ahead in having a better characterization of both such situations. So this is the second way to work out. And the third way to work out, it's an interesting property discovered a few in collaboration with Islam Busada. Islam Busada had the idea, and further developed with Islam and Guillermo Mazzanti during the last years in terms of, let's say, development by using the confluent hypergeometric functions. And this is a so-called multiplicity-induced dominancy. What is exactly this multiplicity-induced dominancy? It's a very simple concept and with a very interesting property that has no equivalent in finite dimension. So the first thing is that we have to revisit the notion of quasi-polynomial degree. And we know that for a polynomial, the degree is nothing else that the power for the dominant term or so on, or if not, we can characterize it in terms of numbers of roots if we take into account the polynomial as being in C. And the other option is just to take into account the maximal multiplicity that a polynomial may have. And this is maximal multiplicity is nothing else than the degree of the polynomial. Such an idea can be also extended, or it has its equivalent in the case of quasi-polynomial. In the case of quasi-polynomial, the quasi-polynomial degree introduced, saying in signal processing, and also discussed in the context of Rolle's theorem by Delonsky a few years ago. So the quasi-polynomial degrees means can be translated as being the number of the sum of the degrees of the polynomials plus the sum of degrees plus the sum of delays. We're talking always about constant delays. The sum of delays, including also the case of the delay equal to 0, minus 1. So there is a result by Poya and Zegio allowing us to make such a concept, such a definition consistent. So in other words, in this particular case, we are talking about the generic multiplicity-induced dominancy. The degree of quasi-polynomial is nothing else than the maximum degree, the maximum multiplicity that the corresponding quasi-polynomial may have. And if we have only one delay, in this particular case, we can show that the generic MID characteristic root, so that means the one having the maximum allowable multiplicity, is dominant in the sense that all the other characteristic roots are located to the left with respect to this root. So this is an interesting property that it was not exploited in the literature in the past. There are a few results, but there are a few results based on trial and error method and not necessarily done into or done by numerics, but not necessarily done by using an analytical proof of the idea of the result. And by using this, so we can, of course, if we are thinking about control, we can have an interesting, relatively simple methodology, which is just developing a partial placement. That means we are just putting all the characteristic roots for the closed loop system at a given value located in C minus, and we have a kind of guarantee through the results developed, the theorem and the proofs. We have a guarantee that all the other characteristic roots are located to the left of this characteristic root. So I've started to use a few notions which are not necessarily have not been introduced. So it's a bit, let's say, it's a bit it appears to be a little bit fuzzy in terms of presentation, that I will try to let's say, to be back to all of this. So to conclude on this multiplicity-induced dominancy, what is interesting is that it allows to relate some concepts which have nothing to do with each other. From one point, we are relating the delay differential equation, and in fact, a particular class. We are talking about the distribution of the characteristic roots for the corresponding characteristic function, and some particular class of second order differential equations which are related to Kammer and Whittaker, and which are degenerate or confluent differential equations having some particular singularities, which are in fact 3 types of singularities. So we are back to the singularity concept idea. And anyway, so it's, if you have the occasion to read the papers written by us, it will be a real pleasure for us to discuss, to further discuss with you. With respect to this last category, there are still results to be developed. Everything is not completely done, so there are still open problems, and there are a lot of interesting ideas that are still to be developed. Now, if I take into account if I try to, let's say, to combine a little bit, we can say that concerning the Weierstrass preparation theorem or the Weierstrass polynomial and the multiplicity-induced dominancy, we can see more or less an idea which is as a background idea, that is, we are factorizing more or less the quasi-polynomial by putting ahead or taking advantage on a particular form of the Weierstrass polynomial. If we are taking into account for the first case, and it's more oriented to the numerics, and the second case, which is the multiplicity-induced, we are more oriented to have to have symbolic computation from one hand and numeric computation from the second hand. There are some toolboxes that have been developed for each of the methods, and I think the most advanced at this stage is the toolbox related to the third method. So this is a kind of, let's say, overview of what are the main ideas that I am intending to present in this talk, and also in the forthcoming talk at the IFAC time delay system workshop. And I think that the introductory part will be more or less similar to both talks. So now, in order to introduce the things properly, to discuss about the Newton diagram, to discuss about frequency sweeping curves and the multiplicity-induced dominancy, we need to go ahead and to have at least an idea about what we are intending to show at the end. So here we have a very simple graphical representation which shows how the roots behave with respect to the delay parameter. You can see that in terms of colors, there are some roots that are continuing their trajectory in a proper way. I'm talking about S1, and there are S2 and S3 arriving, and they are splitting up. So now if we take a look on the characteristic function, you can see that the characteristic function includes what? Includes a polynomial, which is, okay, forget, for instance, the coefficients. The coefficients have been chosen in such a way, we have such an interesting property, and it's not necessarily the case in nature, let's say. Of course, as a bracket, it is clear that when we're talking about the multiple characteristic root, this set of multiple characteristic roots, it's more or less has the measure equal to 0. So we have to, the generic situation is not this one. However, to have a complete characterization of the stability or the complete characterization of the behavior, or taking into account how the roots are crossing the imaginary axis in order to have, as far as possible, a good description of all the stability regions with respect to one parameters, with respect to more than one parameters, we need to take into account the multiplicity of the characteristic roots. So in this particular case, so we have a polynomial of order 5, and we have here on the left, we have more or less 2 delays, one being exponential minus lambda 2 tau multiplied power 2, or twice tau, being with coefficient 1, and the other one being being a polynomial of degree 3. So there are 2 interesting observation that I wish to have with respect to this graphical representation. That I'll show it once more. I'm glad that it works. It was not working a few hours ago. So the first observation is that we'll see a little bit later on that getting characteristic roots on the imaginary axis, in fact, computing the characteristic root on the imaginary axis, we do not need explicitly the delay values. I'm talking about a standard quasi-polynomials. There are other polynomials a bit more complicated. For instance, when the coefficients are depending on the delay parameter, at that moment we'll really need to have information about the delay when computing characteristic roots on the imaginary axis. This is the first observation. However, when we're talking about multiple roots on the imaginary axis, we need accepting the delays and the parameters are necessary to be taken into account for having the real algebraic multiplicity of the characteristic root. So if we try to conclude as a short scheme, first point is that the characteristic roots on the imaginary axis can be computed without using the delay information. And second point, which is the one related to my talk, is that in order to be able to go ahead to have a multiplicity larger than 1, the delay parameter as well as the other parameters become, and the connection between these parameters become essential in order to have roots having a multiplicity larger, algebraic multiplicity larger than 1. So this is one of the observations. And the other observation is that in order to have such a property, we need a structure for the system. So in particular, if we have commensurate delays, it's also true if if the delays are not commensurate. So we have the structure of the system, or the structure of the quasi-polynomial may strongly influence the presence of the multiple roots. A few years ago, during a talk, some of my colleagues asked me, "Can you generate in a simple way, saying a dynamical system having in some natural way multiple characteristics?" And the idea is that, of course, we can generate everything we wish, but in general, the symmetry is the origin of such type of behaviors. And if we are talking about symmetric networks, if we're talking via associative memory, for instance, in networks where we have, for instance, symmetry, some kind of symmetry. So at that moment, we can generate such characteristic roots having multiplicity larger than 1. Of course, now with respect to that, there are various type of configuration in which symmetry will generate only so-called semi-simple characteristic roots. If you take a look at S1 may belong to such a category, so in the sense that it continues its trajectory without any particular problem, and furthermore, we can hope that accepting the continuity of these characteristic roots with respect to the delay parameter, we may have also the differentiability of it with respect to the delay parameter, or with respect to the other parameters. So as a second conclusion, so the first conclusion is characteristic roots on the imaginary axis can be computed without having information on the delay, except in some particular cases. The second conclusion is that we may have such kind of, let's say, type of behavior. So that means with multiple characteristic roots, generally by using symmetry. Of course, symmetry is not the only frame, but it's one of the possibility to have it. Now, in order to fix the ideas, I'm starting with something which is extremely simple, and it's a little bit, it's redundant in the sense that in most of the books you'll find it, but I think that is the easiest way, the easiest way to fix the ideas. So what we are doing, we have a single input, single output linear system, and what we are doing with the single input, single output linear system, we are just closing the loop by using feedback law on the form u of t. It's minus I t minus tau. So in other words, if we are writing it in terms of, let's say, a quasi-polynomial system by using Laplace transform, so we are arriving at a closed loop system, which is nothing else than q of lambda plus p of lambda exponential minus lambda tau. And it's well known that the closed loop stability is equivalent to the spectrum location in C- for such a quasi-polynomial. Of course, we are recovering the classical case if the delay is equal to 0 for having the root location in C- for the polynomial Q of lambda plus P of lambda. So here we are just leaving as 3 parameters. Here it's a P should be a vector, sorry for missing the vector sign, and tau are parameters of the system under the constraint that the tau is assumed to be positive. We can assume that the degree of P it's less or equal than the degree of Q, but in general we are working with the degree of P less than degree of Q, because in the case we have equality, we are in the neutral case, and in a neutral case we have to take into account also the delay difference operator in order to be sure that everything goes in the right way. So I will discuss this issue separately. So the zeros of this quasi-polynomials are nothing else than are called characteristic roots, and we are using the terminology that introduced by Berman and Cook in 1963. So now the fundamental result that we are using, and which is essential in most of the discussion that I mentioned earlier, is the so-called continuity type argument. It's based on Rouchet theorem, but it can be, there are several ways to prove it. So what is simply saying this result is that if we have a characteristic root with a particular multiplicity, let's assume that this algebraic multiplicity is equal to k, then if we are perturbing a little bit the delay parameter, of course, in such a way that the delay parameter stays, saying with the perturbed delay stays positive. And if we are perturbing the other parameters, which are the coefficients of the quasi-polynomial, in such a way that we are controlling by some delta, which is defined function by it's depending on epsilon. At that moment, the characteristic function will have exactly the k zeros multiplicity taken into account in the disk, which is defined by absolute value of lambda minus lambda 0 controlled by epsilon. So this is an important property, simply saying that even if we have a multiple root, this root, we are able to manage what's happening for small perturbation on the parameters with respect to the nominal values for which such a root exists. Of course, there are several options. All these k, the multiplicity, in fact, the splitting will be exactly in k independent and simple roots, but we can have k minus, let's say, n index k, which are simple roots, and the remaining nk being multiple roots, and so on. So there are several options, all these options depending on the choice of the parameters to be taken into account. An interesting conclusion of this proposition was proved in 1982 by Cook, and I think it's Grossman, the authors, V. Grossman. It was a paper in Journal of Mathematical Analysis and its application, saying that, and this result is more general than what they have proved for the second order system retarded type. So that as the delay varies, the multiplicity summation of the characteristic roots in open C+ can change if a root appears or crosses the imaginary axis. So in other words, what we are saying in this, by using this type of argument, this remark, what we are saying is that the most important thing, once we are discussing about delays, of course, as a consequence of the continuity property mentioned in the proposition above, is just simply that there are not roots jumping from the left to the right or from the right to the left without crossing the imaginary axis. So making an analysis on the imaginary axis, it's quite consistent, you know, what's happening later on. So to characterize how the number of unstable roots are increasing or decreasing depending on the way the parameters are changed. So next step is that in this context, it makes sense to introduce the so-called spectral abscissa function, which is nothing else than the supreme of the real part of the characteristic of all set of characteristic roots. We're in quasi-polynomial, so there is an infinite number of of characteristic roots. But since we're talking about analytical functions, we have a lot of simple properties with respect to any if we take a line which is parallel to the imaginary axis, the number of roots located to the right of these lines is always finite. This is one of the important remarks. And if we take a compact set, number of roots inside the set, inside this, inside the corresponding set, it's always finite. So based on this, we have a few properties which are interesting and useful and completely necessary for the whole analysis when we're talking about multiple roots. So the first point is the spectral abscissa always exists. This always exists, it's always finite, and this function is continuous. Of course, the classical frame in which most of these results have been developed is in the retarded case. In the neutral case, when the degree of Q is equal to the degree of P, there are some particular properties to be taken into account. Why? Because the spectral abscissa is not necessarily continuous. So there are a few things to be verified, and I think in the first book chapter of my book with Wim, a lot of elements with respect to this particular situation. So the closed loop stability check, if the spectral abscissa it's less than 0, it's a standard result. Okay, so now, since we are changing the nature when the delay goes from 0 to epsilon to a positive value, so we have to take into account what's happening for a small delay value. So this is more or less what I've started to say a few seconds ago about the fact that spectral abscissa is not necessarily continuous in the case when we are talking about a semi-neutral system. So the continuity for small delay values, there are some mechanisms to be taken into account. The first one is the neutral character of some closed loop scheme, and this always happens if we have if the structure if the transfer function is not necessarily strictly proper, it's only proper. And the other thing is related to the Low's implementation. So Low's implementation, why? Because we wanted just to figure out in terms of control, properly posed schemes. What does it mean? It simply means that the coefficients of the quasi-polynomial delay may appear. And the presence of the delay in the coefficients of the quasi-polynomial may generate some particular problems, changing the continuity property. So in this particular case, we can say that we are more or less in some singular situations, some singular case studies, and we can say that it's another type of singularity, not necessarily that the object is not defined, but the object is changing in terms of character. We are the initial saying the initial nature of the system is finite dimensional, saying that the changed nature of the system is infinite dimensional with the appearance of the presence of, due to the presence of the delay parameter. Okay, so here it's with respect to the neutral character. I will not discuss too much about it. I will just mentioning that excepting the point spectrum that we have in the retarded case, the essential spectrum also arrives, and the necessary condition for having the stability for the scheme, saying for the closed loop scheme, is that the difference operator is stable. And of course, in the case when the spectral radius of the D, saying the matrix D is larger than 1, we have a sensitivity with respect to infinitesimal delay perturbation, and this was largely discussed in the literature. The second property is a little bit more interesting in the sense that by using the standard derivative approximation, what we are generating a closed loop system which is not necessarily properly posed. So I'm taking here an example of a gradient plane mechanism for its simplicity. But in general, we can have more or less, we can use, in the case when we are talking about the proportional derivative, let's say controllers, if the relative degree, let's say if we're talking about LTI, a linear time invariant single input, single output system, if the relative degree is equal to 1, at that moment, if we are replacing the derivative, we are approximating the derivative by the delay difference operator, at that moment, we may have similar situations. Of course, in the gradient plane mechanism, the situation described here, it's in some sense similar to the one appearing in the neutral configuration. And it's easy to see that if we are multiplying with tau the quantity, and if we are trying just to think in terms of, let's say, perturbation, the multiplication by tau, when tau goes to 0, may generate, let's say, that the leading coefficient becomes 0, and in other words, we have a vanishing term with respect to the dominant, the dominant coefficient, and these vanishing terms change the nature of the problem. However, since we are talking about the combination between lambda and tau, it is easy to see in this particular case that if we are replacing the product lambda tau by a new variable, we can have something quite nice and easy to exploit, in the sense that if we are talking, of course, tau being epsilon extremely small, and lambda of epsilon being a characteristic root of the initial characteristic, let's say, characteristic function after the change, when the epsilon goes to 0, we have a particular behavior on, you can see on the screen, which is lambda of epsilon. It's 1 over epsilon multiplied with W0, and W0 is nothing else than a solution of a quasi-polynomial. Quasi-polynomial 5 has a very interesting property, and this is the reason for which I'm insisting a little bit more on it. So if we take a look at the quasi-polynomial 5, of course, it's the first order, so everybody may say that it's not complicated to take a look on it, but at deeper analysis, you can see that 0, it's a solution of this quasi-polynomial. In fact, 1 minus exponential power 0, it's 1. So 1 minus 1, it's equal to 0. So 0 minus 0 gives 0. And surprisingly, 0, it's also a double eigenvalue. So in other words, if we are deriving, if we are computing the first order derivative of p with respect to z, you'll see that p prime of 0, it's also 0. So in this particular case, if we still take a look to the equation 5, we'll have a very interesting story. What's happening with respect to this one is that we'll have a root located, of course, on the real axis, and this root will be locked on real axis as the delay parameters, as the lambda I of gamma in this case. So let's leave gamma in this case as a free parameter. If we leave gamma as a free parameter, and we are assuming the lambda I is real, in this case, so the root will move on the real axis in the sense that it can move from plus infinity, arriving to 0, and 0 will have an invariant root and will go farther to the left and will go to C minus. So why I'm insisting on this issue is that based on that, it can be simply to observe that if equation 5 has a positive real solution, at that moment, the corresponding, let's say, implementation law is improperly posed, and we'll have that lambda, depending on epsilon, will come from plus infinity on the real axis. So we have a kind of singularity, and this singularity is related to a particular property which I was using the terminology locking roots on the real axis. So surprisingly, such a situation may appear also for the for the inverted pendulum, and this particular issue will be discussed during the TDS workshop, and I will figure out a particular example related to this inverted pendulum, and explaining in this particular case we'll have a second order dynamical system, of course with one delay. In fact, we'll have one delay, and in fact it will include two delays, but the second delay is commensurate, since it will be multiple by 2 of the first delay. And in this particular configuration, we'll have a characteristic root located in the origin with multiplicity 3. So before going ahead, I'm still insisting on one point. So if you take a look to the equation 5, so once again, we are talking about degree. If the delay is equal to 0, the degree is equal to 1. Why? Because it's a scalar system. In this particular case, it's a scalar polynomial. And of course, if we are, if we have the particular case, the quasi-polynomial degree equal to 2. For this reason, we have the multiplicity equal to 2. Of course, all scalar linear systems have the degree of corresponding characteristic function in the scalar delay differential equation case as the degree equal equal to 2, but on the other hand, except in the origin, the roots on the imaginary axis, which are not located in the origin, are always simple. So this is an important, another important point, another important remark to point out. So that means that the multiplicity, the maximal multiplicity can be obtained only on the real axis, which gives some further arguments for the discussion, for the multiplicity-induced dominancy that I mentioned earlier. So sorry to stay so long on this one. So in the case of small delays, what I'm to conclude on that, if W of 0 is 0, so lambda of epsilon will converge to the solution of the original system, which is the system free of delay, which is nothing else than lambda I divided by 1 minus gamma multiplied with lambda I. And now if the real part of W0 is negative, then the absolute value will go to infinity, but will go to infinity in C minus, and if it's positive, it will go to infinity, but to C plus. So this is exactly what I was mentioning. We'll have a real root arriving on the real axis from plus infinity, and will lead to some improperly posed scheme. So this observation further developed in a forthcoming paper to the special issue devoted to Vladimir Kharitonov, and that will appear in in the special issue devoted to VID that will be published next year. And it simply characterizes all these improperly posed cases. A small gain argument given below. This is that's important. Let's have a look in these particular cases how things are going on, and I'm just producing what I've already said earlier. There is a root coming from plus infinity on the real axis. There is a particular choice of the coefficients in such a way that we can nicely represent the root as long as the delay increases to where we're going to till around 10. Okay, so sorry, I didn't want to go ahead with this one. So now continuing a little bit with respect to the analysis that just to figure the idea, I will try to be a little bit faster because the time is going fast, and my tendency is always to speak too much. So of course we have two particular effects which are dichotomic, and I think everybody knows that when we're talking about an integrator, it's the integrator subject to a delay. We have a destabilizing effect. In case of an oscillator, the presence of delay may generate a stable behavior for small delay values in some particular configuration, of course. So why I was presenting this example is just to figure out the ideas in order to compute the characteristic groups. The analysis in the case tau equal to 0, the analysis of the crossing with respect to the imaginary axis, and the next step is in this particular case just to take a look to the so-called decision function, which is number 3 is the real part of the derivative of lambda evaluated with respect to the delay value and evaluated at the omega crossing. Of course, the delay should be corresponding to should be one of the delays corresponding to the crossing frequency. And of course, if the quantity is positive, we are going stability, and if it's negative, we are going towards stability. Surprisingly, in 86, Cook and Van der Drischke, Kenneth and Pauline have, when studying a very simple configuration, that means Q of lambda plus P of lambda exponential minus lambda tau, realized that this signal computed independent value. So they realized that, for instance, by introducing a very simplistic function, which is Q of G omega, omega being frequency, absolute value power 2 minus absolute value P of G omega power 2, similar to the first one. So the derivative of this function evaluated at the omega crossing, the derivative of this function evaluated on omega crossing the crossing frequencies. If once again, if we are talking about simple roots, the derivative of this function, its signum is nothing else than the signum mentioned above. So in other words, what was interesting in there are a lot of other things in this paper, but one of the interesting results in this paper from '86, in fact, it was already remarked by Kenneth Cook earlier in '82, but not as in a particular configuration. It was not developed for a general quasi-polynomial case. So that the crossing direction is independent of the delay value. So we are detecting roots on the imaginary axis which are independent of the delay value, and we are detecting the crossing direction in some way independent of the delay value. Of course, starting from this, we can talk about the so-called invariance properties related by shifting, and the fact that in the simple case, all these things are completely independent of the delay parameter. So detecting crossing as a first step, and second step, just analyzing the behavior of the characteristic roots with respect to the delay parameter by knowing that for all the delay values, starting from saying generic, the smallest one, plus 2 pi over omega c being omega crossing, the frequency, the crossing frequency, multiplied with some, let's say, positive integers. At that moment, we can generate all the crossing delays corresponding to the crossing frequency. So now. So the algorithm idea, as I mentioned, is Kuckelmann and Rieschke. I'm not entering into detail for this particular case, which is simply starting for, we are simply in the configuration that we have only one delay interval guaranteeing stability. And I will go directly to the simplistic idea that we can have for frequency sweeping curves. And in this particular case, what I've considered first order system in closed loop with a delay block defined by the gain k and by the delay tau, and we are arriving in a closed loop of the characteristic the characteristic equation being lambda plus a plus k exponential minus lambda tau. So what we have done earlier, we consider that lambda equal to g omega, where we are working with respect to the imaginary axis, detecting the existence of characteristic roots on the imaginary axis, and of course, depending on the value of a and k, which is, we are in the scalar system, and I think that scalar system is well managed by now. We can have various configuration types, and these configuration types are represented more or less graphically in this in this graphic and in this figure. And what we can observe, we have the main ingredients of the so-called frequency sweeping tests, in the sense that we are just representing the transfer function, which is defined by 1 over g omega plus a, and of course multiplied k over g omega plus a, which is nothing else than absolute value of k over square root of a squared plus omega squared. And we're just representing the intersection between this function and the unit circle. Indeed, in order to have a root, what we need is more or less exactly the same thing. Exponential minus g omega tau is nothing else than absolute value equal to 1, because we are directly on the unit circle if we are leaving omega and the delay parameter being free, with the assumption that the delay is different from 0. And in other words, what we are just checking, we are checking the situation in which there is intersection between this, let's say, frequency sweeping curve and the unit circle. So intersection in the sense that we can see that for small values, we are inside the unit circle, we are in the so-called hyperbolic case, and if a is positive at that moment, we are in so-called stability situation, delay independent stability. We have a limit case. We are still in the delay independent case, but it's a weakly delay independent case. And we have the other case in which we are crossing the unit circle. And if we are representing such a curve, we can see that in order to establish if the crossing is towards instability, is just the curve goes intersect the line the ordinate equal to 1 up to down. Why? For a very simple reason, 1 over or k over g omega plus a, when omega goes to infinity, goes to 0. So if it's located, it should be located when the omega goes to 0, go to an absolute value to infinity. So it should be located up with respect to the line of ordinate equal to 1. So I think that I don't have enough time to do all the things that I was trying to work out. Here I'm just presenting what's happening in the in the oscillator case, and I think that I'll go directly. I feel uncomfortable, but I'll go directly to a kind of conclusion in order to leave more time for questions and also not to take too much time for the other discussion of the group. And here, sorry, no, this one. I will go back to this one. I will go back to this one, and I will perhaps present a simple result from the non-semi-simple case. This was developed with Ji-Chen a few years ago. In fact, in 2010, the paper was published by Sam Journal of Control, in which we have an explicit construction if we have a non-semi-simple root. Non-semi-simple root, and we are assuming that, in fact, we have a complete characterization of the splitting property with respect to that. And fortunately, I cannot enter into details about the construction. Here it's example that I will not present, and I am coming back at the multiple eigenvalue for the system that I presented just at the beginning. And by using this time the previous approach, and in fact Weierstrass polynomial based methodology, we will have an explicit computation of the lambda 1, lambda 2, and lambda 3, as you see, with respect to the critical delay value, which is equal to p, once again pi. Once again, the construction was done in such a way that we have such a configuration. We have in us, we are more or less with lambda 1, everything is differentiable, so it's like a simple root. This root, it's continuing, it's just conserving the direction of its behavior. In the case of lambda 2 and lambda 3, what we have a square root of tau minus tau star, and this gives more or less the fact that we have a particular splitting configuration. So once again, I'm a bit frustrated not having enough time to enter in presenting the parameterized linear relay system, and we're talking about crossing characterization. And but I prefer that not to give directly the overview without having a kind of introductory material with respect to the ideas to be developed, and to give also only some hints. Of course, in terms of questions, I will be able to answer to a larger spectrum that the stuff that I presented. Now, with respect to TDS workshop, the presentation will start more or less not with any variance property, but will start more or less at the end. At the end of the introduction. We'll start with this example, and after we are, I'm going directly to separating the three categories and introducing in a quite fast way, not necessarily the main ingredients, but directly the results, and explaining these results through examples. For all these examples, I will have other two examples that I mentioned throughout my presentation, which is the scalar case with the double root at the origin, and saying the inverted pendulum with several configurations of inverted pendulum, having a double root at the origin, also having a triple root at the origin. And in the case, we'll have only two delays, which are not necessarily commensurate, and making a few distinctions between all of these. Thanks for your attention. I'm really sorry for not being able to cover all the things that I was expecting to do, and I prefer that. Of course, I'm answering to the question, but I prefer that I'm trying to respect the time constraint.
Yes, thank you very much, Silviu.